title of this project is Remote Control Electric Vehicle with Perimeter Monitoring System. The aim of this project is to design and develop a scale remotely controlled electric vehicle with monitoring system for battery voltage and vehicle speed. The vehicle must meet certain demonstration criteria. Okay, next for the abstract. First, automation or automatic control is the use of various control system for operating any equipment or device, such as a remote control toy car, switching on telephone network, and other useful activations with minimal or reduced human interventions. Second, remote control electric car have been popular for decades. So there are many parameters that have to be studied in the process of operating the vehicle. Third, the method used by SolidWorks simulation software to analyze the structure analysis and the suspension analysis is by using the finite element method. And lastly, the mechatronic harness connection were identified using magnet simulating and freezing to simulate the block diagram systems and wiring connection and Arduino code. Okay, next for the introduction. First, the design and analysis in the engineering sector are particularly important in research and new product development. Both need to match the product specification of definition and necessity in engineering. This is because the product has to keep up with the demand and prospect of the customer. Product design is the process of finding business needs, clearly defining the problem, designing a suitable solution for the problem, and validating the solution with actual users. Designing is the first in the process of the product creation to fulfill the product design goal of addressing the problems that occur. Okay, the aim of this next we will design and develop a scale remotely controlled electric vehicle with monitoring system for battery voltage and vehicle speed. Okay, it can be very complex design process. Sometimes the issues cannot be specified in a detail from a full analysis, and the detail on the design are uncertain. There need not be a solution to the problem. The problem formulation must be developed on numerous occasions as part of the design process. The vehicle must meet certain demonstration criteria. In this project, there are four main systems which are structure unit, suspension system, powertrain, and steering mechanism. For every system and the full assembly product, we will discuss and show the mechanical and mechatronic analysis. The vehicle must meet certain demonstration criteria such as product description, specification, PDS, and engineering requirement. Okay, next. This is needs and requirement. There are 10 of needs and requirements that should be focused to do this car. First, safe, install bumper and barrier. Second, long lasting, medium capacity battery and lower output produce. Third, need wiring, special compartment for electric components, for durable or adaptable. Install suitable suspension and with easy to navigate. To click simple navigation button. Next, lightweight, use lightweight materials, attractive design to design the produced, and the requirements is minimize complex parts, and furthermore cheap, use recyclable material, and finally high stability, low roll center and gravity. Okay, this is our complete system integration. As you can see, this is the isometric view, and this is top view, and this is the side. And under this part, actually we have the powertrain system, which consists motor and gear with shaft, and we have provide 3 suspensions, spring, which two added in front of the car, and another one was behind the car. The 2 spring in front of the car was assembled in vertical positions besides the front of the chassis, and one at the behind was in horizontal position above of this part. Other than that, in this chassis, we have put the battery and the Arduino, also the wiring and so on. And this is how our car look like for this project. Thank you.
Okay, Assalamualaikum and hi to everyone. So my name is Muhammad Arifuddin bin Azizan. So I'll be presenting about chassis analysis of our group. So this is the the model that we come out with a material properties of, we can see here, model type is linear elastic isotropic, and all with this criteria, the tensile, elastic modulus, Poisson ratio, mechanicity, and also shear modulus that is applied based on, that is found and applied that on our chassis model. So this is next, we go to the component weight. So this is the component that found, and this is the weight in kilogram. Actually the unit is kilogram. So with the body weight around chassis is 0.963, and all of the electronic appliances, actually not electronic component, electronic component that is found inside the body of body weight of the chassis. So this is the weight of the component. Next, we go to the loads and fixture for flat surface and also inclined surface. So we can see loads and fixture for flat surface and also the inclined surface is a fixed hinge with the three faces. There is a fixed hinge. Okay, this is the fixed fixture image with the 3 faces entities. Same thing, fixed hinge with a component XYZ because it's in 3D. So with a reaction force and the resultant, different type of resultant for flat surface 0.529223, and for inclined surface is 0.529433. And for the load, we have 3 type of load: force 1, force 2, force 3 for both flat and inclined surface. So this is the image. Actually we can find the force that is applied, actually the load image that is applied, different type of load that is applied, force 1, force 2, force 3, with a different value that is obtained actually from force 1, force 2, force 3. For flat surface, we found that 0.245 for force 1, 0.0784 for force 2, and force 3, 0.206, all in Newton. For inclined surface, we found that 0.0784 Newton for force 1, 0.245 for force 2, 0.206 for force 3. Now, we go for the analysis on flat surface. Okay, for analysis on flat surface and also analysis on inclined surface, we have three analyses actually, which is stress, displacement, and also strain. Okay, based on stress analysis, displacement analysis, and strain analysis, we can found that the types of the stress for inclined and also flat is von Mises stress with a minimum, the same minimum, all with the same minimum is 0.0 Newton meter power of 2 with a different maximum actually. For stress analysis in flat surface, we found that 8.51 exponent of power of negative 3 Newton meter power of 2 actually for maximum. It's quite smaller than the stress analysis on inclined surface with a 7.855 exponent of negative 3 Newton meter power of 2. So there is a big changes on stress analysis. So from this picture we can see that this is the isometric view and this is the bottom view of the chassis body. So the color is the blue is the minimum and goes up until red, which is maximum. So from here, from isometric view for stress analysis, it's quite the same for flat surface and also for inclined surface. So we have 3 hinge with intermediate value of stress actually, because these 3 points is where the suspension is connected on the chassis actually. The suspension is connected in these 3 points. So there is intermediate value of stress changes on these 3. So on the bottom part you can see there is color changes between the light blue and the light blue actually around 0.518 to 1.704 exponent of negative 3. The color changes on this stress analysis. It's the same thing for stress analysis on the inclined surface. A bit changes, colors is the same, but only changes is the maximum value. And for displacement analysis, we can see quite big changes. Also the same or for flat surface and also inclined surface displacement with type is the same, resultant displacement with a minimum of 0 millimeter and maximum of 2.24, but changes of maximum in inclined surface, which is 2.039 exponent of negative 4 millimeter. So the value, the color changes is quite different actually, but we can see more on the bottom part of the view. So from the minimum to the maximum, from the outer from the side, the outer side of the chassis into the middle part of chassis, there is quite big changes of displacement actually. This is for displacement. And for strain, also the same type for incline and also flat surface with an equivalent strain, minimum of 0 strain and also maximum of 1. For maximum, there's changes for flat surface and inclined surface. For flat surface, the strain is 2.2327. It's quite power of negative 6. And 1.372 exponent of power negative 6 actually. So on inclined surface there is less strain, a bit less strain than for uh, flat surface. So the color changes also the same. We cannot see actually for strain and stress based on isometric, but we can see more clearly on the bottom part of the chassis body. The color changes. The same thing on strain analysis for incline and also flat. The changes color is around blue to light blue. This is below intermediate. So that's it from me. Thank you very much.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Today I am going to present about the suspension analysis for our remote control car. And this is our suspension system, which consists of two springs connected to the body of the chassis here, and the body of the steering part. These are the material properties for our model, for our suspension analysis model. We use the ABS PC. The tensile strength is 4 to the power of 0.7 Newton meter square, elastic modulus of 2.41 to the power of 9 Newton meter square. Poisson ratio is 0.3897. Mass density is 1070 kilogram per meter cube. Shear modulus of 8.622 to the power of 8 Newton per meter square. So loads and fixture. The first fix is here at the suspension, which are connected to the steering system. And the second one is here, the green one, where the suspension system which are connected or being held by the chassis system. And on the cylindrical faces, we use this part here, the blue one, to allow movement this direction and also this direction. And these are all the resultant forces for those features. And for the load name, we apply the force to the cylindrical part here, the bottom part of the suspension system, and the value is 0.2594 Newton to the X, Y and Z direction. For the spring connector, we use the spring connector to stimulate a spring here, and the stiffness value is 535. Spring connector 1 is for suspension number 1, and spring connector 2 is for the suspension number 2. Moving on to the result. These are the results for the suspension system. The von Mises stress is maximum at 7.209 E to the power of 4 Newton per meter square. And the critical part is here, where the force is applied. Okay. So next is for the displacement of the suspension system. The maximum displacement is 1.277 millimeter. And the critical part is here. This is because the body of the system has more weight on the right side. Okay, this is from the front view. And also the strain, the maximum is 2.41 to the power of -5. And again, the critical part is here, the right hand side, because the weight of the component is more on the right hand side. Okay, this is the critical part. For the spring analysis, the mass of the spring is 0.0286852 kg per spring, with a density of 7,100 kilogram per meter cube, and the weight is 0.281115 Newton. And for the spring, we use the material ductile iron, and the yield strength is 5.51485 e to the power of 8 Newton per meter square, tensile strength of 8.61695 e to the power of 8 Newton meter square, and other parameter. So these are the results of the simulation for the flat surface and for the spring inclined surface. For the spring inclined surface, we incline the model to the 30-degree force, and for the flat surface is flat. Okay, for the stress analysis, von Mises stress, the maximum load applied on the spring is 3.284 to the power of 7 Newton per meter square, and the critical part is here, the right hand side. And for the we apply the force here and also made a constraint here. Okay, and for the spring incline 30%, the von Mises stress, maximum von Mises stress is 3.612 to the power of 7 Newton per meter square, and the critical part is down here. Note that the difference between two spring is the distribution of the stress analysis, and when inclined, the stress is more down here compared to the flat surface. The stress distribution is almost the same linearly. For the displacement of this spring, for the flat surface, the displacement is 1.317 millimeter, and the maximum displacement is on where the force is applied, which is here. Same goes to spring incline 30 degree, but the displacement of the spring is 1.252 to the power of 1 millimeter. As you can see, the flat surface has more displacement compared to the inclined surface, and we applied the force 30 degree to this plane number 7, with the body, the weight of the body and the weight of the component. And the strain analysis for this, and the strain and the equilibrium strain for the spring analysis is 2.054 to the power of -4 for the flat surface, and 2.250 to the power of 4 for the spring inclined surface. The strain is higher on the inclined surface compared to the spring flat surface, and the critical part for the equilibrium strain is the right hand side of the car here, and for the inclined surface it is as same as the stress, which are down here. Alright, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ibrahim Zulkifli. So I will present my part. So first is grade ability. Grade ability is the ability of a car to travel on a slope surface. In this slide, there is the free body diagram of a vehicle that travels on a slope. So next is the table. The table is actually the list the data we extract from our vehicle our own vehicle, which is mu is 0.8, L is the length of the wheelbase, which is 20.385 centimeters. A is 10.4175 centimeters, B is 9.965 centimeters, and H is 4.052 centimeters. So next, the adhesive, how we get the gradient for our car. So this is the formula we use to find the gradient of our car. We actually extract them from the derivation or from the free body diagram of the car that I mentioned earlier. This is in the previous slide. So the formula is the tan theta equal to mu minus k over L minus mu. The that the the data to determine is actually the theta itself, which is the is the gradient of the surface. So after we put the data on the formula, we got that the theta is 25.926 So this is the maximum gradient that our car can travel. So next is the maximum speed. So the maximum speed was analyzed in two different conditions, which is first is flat surface and second is gradient surface. So first flat surface. Before we find the maximum speed, we need to know the power of our vehicle that travel on the flat surface, which is in this case for flat surface we use the aerodynamic power and rolling tire power. Actually there are one more power we need to consider, which is the gradient power. But on the flat surface we actually ignore the gradient power because there is no gradient on the flat surface. So uh, in this table we is actually the parameter that we will put on the formula I mentioned earlier. So next, the first is the rho. The value is 1.25 kilogram per meter cube. Next is CD, which is drag coefficient, which is 0.05. A, the contour area is 0.0154 meter squared. A is 0.012, B is 0.00004, and this is the mass of our Arctica, which is 0.794 kilogram. The grade is the gravity acceleration, which is 9.81 meter per second squared. So this is a graph of our engine speed. To get this graph, we use a variable of velocity so that there is the trend of our graph so that we can know the speed of the max speed on the flat surface. So for on the vertical side, which is the power, it's actually the summation of the aerodynamic power and rolling tire power. And then the horizontal side, which is the x-axis, that it is the variable of velocity we use. We put on the formula so that we can know the power value. So the range of the velocity we use is 0 to 50 km per hour. So how we get the maximum speed when on the flat surface is based on from the power output of motor we use. Actually, the motor power output we use, the maximum is 1 watt. So when on our vehicle, when 1 watt of power motor used, so the maximum speed on our car is around 27 kilometers per hour. So next we are the gradient surface, which is incline of 25.96 degree, which is the reliability of our car. So in this part, before we calculate the maximum velocity, we need to know the value of power. The power is aerodynamic power, rolling tire power, and gradient power. It's same with the flat surface, but we add the gradient power on this part. So the parameter we use actually the same on the flat surface too, but there is additional of uh, data, which is data which is the value is 35.96 dB, that uh, that you can look on the bottom of the table. So next is the graph power against speed. Actually, the concept to find the maximum speed is actually the same from the flat surface. I show you here. The power is actually the y-axis. The power is actually the summation of aerodynamic power, rolling tire power, and gradient power. So in this case, the velocity, the range of velocity we use actually quite small. The range is 0 to 4 kilometers per hour. So as you know, we use the uh, one watt of motor on our car. So when 1 watt of power we use on our car, so based on the graph, we get we got the maximum speed 0.25 kilometers per hour. So our car can travel 0.25 kilometers per hour on ready surface when 1 watt of power motor use. So that's all for me. Thank you.
Okay, Assalamualaikum. My name is Muhammad Shamil Fahmi, and I will explain about steering system. First of all, let's look at the design of the steering system. This is our first attempt on on the design making. There are two designs that we have developed. The first one is the from basic Ackerman steering rack, and the second one is from the basic rack and pinion. So to decide on the design that we want to develop, we should compare the design first. So this is the table comparing the design 1 and design 2, which is design 1 is the Ackerman steering rack, and design 2 is rack and pinion. So the weight of the first design is light, and the second design is a bit heavy because of the component, the rack, the gear, and the motor. And the suitability with the suspension design is design 1. We found that the basic Ackerman design is not very suitable to fit into the our full car assembly, while the second design, the rack and pinion, is almost completely suitable to be developed and fit into our full car assembly. Now, for our decision, we choose the rack and pinion system. This is because the rack and pinion system is commonly used in steering system of car to convert the rotary motion of steering wheel into rectilinear motion of the wheels. The next one is because it provides gear reduction, making it easier to turn the wheels. And the last reason on why we choose the rack and pinion system is because since the design is electric car using motor, it is easier to make a rack and pinion movement as the motor connected to gear, and gear will become the pinion to rotate the rack. So for our concluding design, this is our final choice. After we remodel the second design, we added the chassis system. The structure system is supported with chassis, and it is suitable with the suspension design. It is more robust and reliable. It is quite heavy, but the heaviness, the weight of the chassis will make the overall car to be stable. We have divided the design specification into three components, that is rack, pinion gear and wheels. The rack has a length of 24 cm, has 25 teeth, and the thickness is 1.2 cm. The pinion gear has a diameter of 3 cm, has 30 number of teeth, the thickness is 0.3 cm, and the center shaft diameter is 0.2 cm. While the wheels have the overall diameter of 4 cm, the rim diameter is 3 cm, and the wheel base is 20.4 cm. Next, we look on motion analysis. The objective of motion analysis is to determine the minimum turning radius of the RC car. The conditions are such as it is on a flat surface and maximum turning of steering wheels. We use SolidWorks to do the motion analysis. As we can see on the top left, the figure is a demonstration about how the wheels will be rotated. And also, this is the top view showing the maximum angle turning of the wheels. So we get, from the SolidWorks, we get the maximum turning angle is 21.7 degrees. The turning radius is given by the formula of RT is equal to B over sine theta minus A minus C over 2, where A is the distance center to center between two wheels, B is the wheel base, C is the length of the rack, and theta is the turning angle of wheels. Next is our schematic diagram about our car. From the given formula from the previous slide, we calculated the value of the unknowns A, B, C, and theta from SolidWorks, and we get that A is equal to 32.6 cm, B is 20.4 cm, C is 24 cm, and theta is 21.7 degree. Plugging all the values into the equation will give us the turning radius. And since the theta is the maximum turning angle, so we will get the minimum turning radius of the car. That is 50.84 cm.